Imagine a single server rack drawing 1.5 million watts of power. Yeah, 1.5 million. That is not an entire building, folks. That is just one single rack. And by 2028, this is the projected physical reality of the cloud that's powering artificial intelligence.
Welcome to This Explainer. Today, we are taking a high-tech anatomy tour straight inside the modern data center. We're going to map out the incredible physical infrastructure, the hardware, the massive high-voltage power lines, the cooling pipes that actually make AI possible in the real world. Here is our blueprint for today's tour. We'll start with the new AI factory, zoom into the brains, explore massive power distribution and keeping it cool, and finally wrap up with the nervous system. Section 1. The new AI factory.
Okay, let's dive into this. It is really easy to think of AI as just software floating out there in the ether, right? But the physical reality is vastly different. Look at a traditional CPU-focused server rack. It uses about 10 kilowatts of electricity. But these new AI data centers, they are packed with high-density accelerators, demanding 60 kilowatts or more per rack. It is a completely different scale of computing. Just look at these massive rows of high-density server racks. Packing that much sheer computing power into such a tight physical space? Well, that creates massive thermal and electrical crises. You simply cannot build or run these new facilities the way we used to run standard server rooms. It's a whole new ballgame.
Section 2. The brains. So zooming in from the macro facility down to the highly specialized microchips that are actually doing all the intense AI calculations, we basically have two main players. On one side, we've got GPUs, or graphics processing units. They are incredibly versatile, they support a really broad range of frameworks like PyTorch, and they're great for mixed workloads. On the other side, we have TPUs, or tensor processing units. These are application-specific circuits designed by Google. They are purpose-built strictly for tensor operations, which makes them highly efficient for training large language models.
But here's the catch. You have to feed these hungry AI brains, right? And that requires specialized memory. Specifically high bandwidth memory, or HBM. Now, producing a single bit of HBM requires roughly 3 times the wafer manufacturing capacity of standard DDR5 memory. 3 times! Because of this massive physical requirement, the AI boom has actually triggered a global supply shortage in semiconductor manufacturing.
Section 3. Massive power distribution.
Okay, we have the brains. Now let's look at the metabolism. We need staggering amounts of electrical infrastructure just to keep those specialized chips firing. Let's look at the absolute engineering nightmare this creates. If you try to distribute just 1 megawatt of power using a traditional 50-volt architecture, it requires a staggering 20,000 amps of current. Trying to push that much current through traditional bus bars would require copper that is unimaginably heavy, expensive, and dense. Actually, scratch that, it literally wouldn't even fit inside the rack. And this brilliantly illustrates how engineers solved that exact crisis. By switching to an 800-volt direct current bus architecture, they reduced the current requirement from 20,000 amps down to a highly manageable 1,250 amps. This massive boost in efficiency shrinks the amount of copper needed and frees up crucial physical space in the server rack for, you guessed it, more processing power. Zooming out to where all this power actually comes from, this isn't just happening out in remote areas. These demands are actively straining local grids in everyday communities. To meet this need, facilities are largely relying on fossil fuels like natural gas peaking plants, and in some regions, utility companies are even unretiring older coal plants. It is definitely worth noting here that this rapid infrastructure build-out has seen active support from both the Biden and Trump administrations. Both recognize the strategic importance of AI data centers, regardless of the ongoing environmental concerns surrounding these energy sources.
Section 4. Keeping it cool.
So all that massive electrical power instantly turns into intense heat, which absolutely must be removed before the chips throttle, slow down, or literally melt. Because standard air cooling just isn't enough anymore, the industry has shifted to liquid cooling, specifically direct-to-chip cold plates. It's literally, as the quote goes, like the radiator in your car, jumping into a cool pool on a hot day. Pumping water glycol mixtures directly to the chips is far superior to blowing air because liquid just absorbs and transfers heat so much more effectively. Now, what's really interesting about this is how it creates a continuous, closed-loop thermal dynamic. Let's walk through it. First, heat absorption happens right at the cold plate on the processor. Second, that heat is transported via a network of tubes to a coolant distribution unit. Third, heat rejection takes place at a heat exchanger, which moves the thermal energy out to the facility's main water loop. And finally, the chilled coolant returns to the servers to do the whole thing all over again.
But this cooling process operates on an unbelievable scale. Take a second to let this massive number sink in. According to a Department of Energy report, by the year 2028, data centers in the United States alone are projected to use nearly 80 billion gallons of water per year. 80 billion! That is enough to supply hundreds of thousands of households, and it's primarily driven by the rapid proliferation of these incredibly hot AI servers.
Section 5. The nervous system. All right, we've covered the brains, the power, and the cooling. Now, how do we link all these individual processors into one massive, coherent supercomputer? Well, it requires a hybrid network approach. Inside a single rack, a technology like NVLink handles ultra-fast communication, effectively uniting dozens of GPUs so they act as a single, shared memory brain. But to scale out and connect multiple racks together to form those massive training clusters, the system relies on high-bandwidth fabrics like InfiniBand and Ethernet. But hey, even with those cutting-edge AI fabrics doing all the heavy lifting, standard RJ45 and management ports show us that traditional Ethernet still plays a totally critical, foundational role. It handles the storage data, the telemetry, and the external facility management that keeps the entire factory running smoothly behind the scenes. Let's move to this matrix and see how this all builds together. When designing these networks, the sheer scale of the AI factory dictates your technology choices. For a smaller cluster, under 100 TPUs, the cost savings of Ethernet make it the clear choice. But scale up to a cluster of 500 to 2,000 GPUs, and InfiniBand becomes the go-to for its automation and stability. Go beyond 10,000 GPUs, you're building a complex hybrid federation of mixed networking technologies. It's an absolute puzzle at that scale. So what does this all mean? We've seen the staggering requirements of these new AI factories today, from megawatt power distribution and liquid cooling loops to massive, massive land and water usage. It leaves us with a critical question to ponder as we move forward. As AI infrastructure consumes such massive amounts of power, land, and water, how much of the physical world will we ultimately dedicate to the digital one? Thank you so much for joining me on this explainer, and keep questioning the infrastructure around you.